be a simple solution.
I know. Was that?
Did Min talk to you about posting discussion notes?
No.
Okay, her plan was we're going to just post like her own notes for the previous section too. For now, I'll just write up the examples that I have.
Okay. Sounds good. Next Tuesday after. Okay, good morning. Let's get going. All right, first I want to thank you all for responding to mid-course evaluation. I think that was a really good thing to do. We got a lot of useful comments from you, and I think we took notes. We know what are the things that you would like us to improve, and we'll certainly do our best to change that for the rest of the semester. And I encourage you to keep using that account, send us feedback. If there's anything we can do, we'd be happy to assist. A couple announcements for today. I will talk about Project 1 briefly, and make sure you start early on this project. 1 week won't be enough to finish this project. Sign-up sheets are up in 353 lab, and we will pick up sign-up sheets after today's lab session, and then we'll figure out if there is anybody who still needs a project partner, and we'll try to team you up if you can't find a partner or if you have any concerns. Project groups are identical. It doesn't matter which group you assign for. It's basically the same, exactly the same problem with just slightly different parameters, so you don't worry about that. For the labs, we feel that there is still quite a number of students who didn't have a chance to finish their software labs, so we extended the software labs to this week. And you can that will give you a chance to finish lab number 6 or any remaining software labs. So just get that out of the way, pick up graded labs from 353, and then next week you can basically just have all the labs behind you and work with the project. Next week we will be able to help you with project during the lab times. So all 4 of us will be there, basically standard Monday, Tuesday, Thursday, and Friday discussions. I'll show up in Thursday lab. And make sure that you start early enough on the project, and then you have good questions. By then, you should be almost finishing up by then, basically doing SPICE verifications and things, and we'll be able to help you a bit with that. Homework 6, we extended the due date to next Monday because some of you have E142 midterm. If you finish early, that's great. And there'll be no new homework posted this week. Okay. And another important change will be with regarding my office hours. So I've realized basically that there is a couple of issues here. Basically, a lot of you are taking E140, especially undergraduate students, and Wednesday 11 until 12 you have lectures, and that doesn't work for most of you. And also, we sort of had this office hours, to say in E141 terms, in the critical path of the homework. So basically, you spend a lot of time in the office hours asking questions about homework, and there isn't really enough time because this is a big class, and there isn't enough time for everybody to really clear out all the issues and basically sort out all the conceptual things, methodologies, and so on. You should still ask questions about homework. Don't get me wrong, but still, I feel I should give you better time so that you can all attend. I looked at the schedules for 140, 105, 142, and this was the only time that basically didn't collide with any of those activities. And since, as I said again, this is a pretty sizable class, another thing that I'm going to do is basically, in addition to office hours, instead of having 2 office hours per week, I'm going to run a bi-weekly review sessions starting this Thursday. So what we are going to do is basically the same thing that we did for the midterm, and those will be 1-hour review sessions. So basically, I'll be there, and you can ask me any questions about class material and so on. And that way, I think we can pretty much balance all the needs that you have for the homework during that week, and also to catch up with the material. And to keep this synchronized with the midterm schedule and stuff, I'm going to start this week. And other reason why I want to do that is because I would like to give you some time to digest the project and get started, so I can eventually help you with some project ideas. So that's going to be every other Thursday. I still have to figure out the time and location, but I'm guessing I'm thinking to do it sometime in the afternoon, like 6:30ish or so, when you have all your other things done. And would that work? Okay, so good. Those are the things that are going to change. So let me now give you some hints about your project. So this is what you're going to do. And using the material that we covered so far, this is going to be really interesting for you. And this is a design problem that is both relevant and practical, and also it has enough academic challenge to it. So when you go to, if you are looking for a job after this semester or next summer, and you go down for an interview, make sure you mention this project and explain to people what you have done. They will really appreciate it. So here's what it's all about. So basically, you assume that you are designing a large system. And in order to deal with large system, as we hinted so far, it's a good idea to do hierarchical design and sort of figure out design blocks A, B, and C. And since chances are that these design blocks will have different complexity, what's going to happen is basically that in order to distribute a clock tree, you would have to see a different clock load in each of these domains, which is represented by the number of these parallel branches that you have in each of these domains. So basically, you assume that each of these buffers can really reliably drive only a certain number of flip-flops. Let's say CL was 16 in this case, so maybe that's about 30 flip-flops or so. If you drive more, then you have problem with slopes and things. You don't want to do that. And due to varying complexity, you have basically different sizing factors over here. So now let's assume that you have done designing all of these blocks. And now the question is, well, but these need to work at the top level. So I need to really tune a little bit my clock tree to make sure that I have the same delay, propagation delay, from my external clock that comes in here to all the clock nodes over here. Because what you really want to do is have a perfectly synchronized system. So you have basically all your clock edges aligned such that when your signal travels from block A to block C, you still have well-defined reference points for those signals. So that's basically the idea. And so the first question you will be asked is basically to pick the sizes of all these buffers such that you have minimum insertion delay, so-called. That's basically simply propagation delay from the clock to all of your nodes satisfied. And now, basically, we know that minimum delay comes at a certain cost. So it's basically highest performance you can get, you're burning too much energy. And then the next question I'm going to ask you is basically, okay, let's assume we don't really need to be that precise. I mean, we can tolerate some little bit of skew between delays in blocks A, B, and C, and then still have a good timing. And then basically the question would be, if you are given these skew budgets, you first need to determine, based on the size of the blocks, which skew number you're going to assign to which block to make sure that you have optimum energy, minimize your energy. So it's basically giving you a little bit of timing slack, but reducing energy. It's the same like if you are basically driving a Ferrari. That's basically like the highest speed you can get, but it's really expensive. So you can say basically, well, I can settle for the BMW. It offers me plenty of performance, but it's more affordable. So that's kind of the trade-off that we are going to do. But let me get you set up with minimum delay problem over here. So what you need to do now is basically you have these different clock domains. So you notice that if you want to minimize the delay in the worst case, so basically the fair thing to do is basically think this way. If I want to minimize delay in all of the branches, then all of them should be treated the same way. They should have the same fair treatment, meaning that the optimal result would be that delay in all of these subdomains is equal, right? Because if it's not equal, some delay is a little bit longer, then you can still tune the other blocks to sort of make the delays equal and trade off energy consumption, right? So that makes sense. Is that clear to everybody? So now what you are going to do is basically say, well, now I know that delay, for example, through this network should be equal to, for example, from the clock to this node, to that node, and so on. So since the delay is through all of these nodes basically is equal, what this means is that all of these y's have to be the same size, right? Because from this point to this point, delay is equal as from this point to that point, right? So that makes sense intuitively, right? And then you simply have a model of this network as we developed in the homework. So basically you have, over here you have x3, and then you have this branching business that you're going to understand also later during today's lecture. So you have, basically you say that you have n3 identically sized buffers y3. Okay, so that's basically just to develop a model for hand analysis. And then this is your load capacitance. And then you have other two branches in the same way. So you have x2, then you have y2. This is your load, and this is branching n2. Same thing for x1. And then you have n1. And finally, you have the state size of this one fixed, if this is your clock. Now, the key point over here. Okay, everybody following? So now, since you have imbalance in the load in each of these branches, because the total load from the capacitance is different, you are not going to have equal x1, x2, and x3 that will balance your delays. That is basically the major deviation from that branching theory that we did. And basically, I'm going to teach you later in this class that basically branching theory, although that theory has been developed at Stanford, I'm not going to say it's wrong, but it holds under certain conditions, okay? So what you actually imply in that branching is when you apply this branching factor, you assume that the size of all of these parallel branches is the same. So if you develop a model over here and say, I have my clock buffer size 1, then I have some x's are all equal, and then you have branching factor of 3, that's not correct. That's not going to give you the good answer, because the problem with this branching is basically that once you have this off path, then you don't know, you have no longer control what's going to happen to the delay of that path. You just forget it. That's some fixed capacitance sitting there. I don't care about this delay. But in this case, I do care, because I have this off path over here. If I just analyze this path individually, then I have this off path that has to have the same delay as my critical path. So make sure you include that in your analysis. And then I'll give you a little bit more of a hint there. So if you are asked to minimize the delay, it's good to start from the delay expression, right? So you have basically that your delay is equal to Tp naught, 1 plus x1 plus x2 plus x3 divided by gamma, plus Tp naught, and then you have 1 plus basically your branching delay, bk times yk divided by xk, and then finally you have the third stage, Tp naught, 1 plus cl divided by yk. Now, this is the propagation delay tpk for each of the branches. So you basically have 3 different branches over here. So you have basically 1 branch, 2, and 3. And then you say, if this is my delay of a branch, delay 1, this is delay 2, and this is finally the delay 3. So now you are basically looking at 3 delay parameters. And what you can do now is that say, well, my worst case delay is equal to the max of D1, D2, and D3. And what you need to do is basically minimize this D. That's the goal. So now later today I'm going also to post you some hints how to do this mathematically. Question?
How come only the first one has gamma?
That's very good. Thank you very much. All of them have gamma. Thank you. So you can do this basically in MATCAD or MATLAB. Use any CAD environment that you're familiar with. So I'm going to give you some hints for MATLAB, which I think you all have access to. So what you basically need to do here is just use any function in MATLAB that minimizes certain objectives. So what you need to do is basically develop this model. Say I have a delay function that returns the values of these 3 delays. And then I say I want to minimize that, given these parameters x, which is in my case x1, 2, 3, y1, 2, 3. So that's basically you have a vector of 6 parameters, 6 variables, and you need to minimize the overall delay. Okay, everybody clear with that? And then for the other part, now comes the fun part. Try to get this minimum delay as soon as possible. If you can get it by Thursday and then we can compare notes, that would be good. If not, I'll give you more help. Just make sure that you spend some time thinking about it and that you're going in the right direction, because the next phase is the optimization phase. That's going to be really interesting. So now what we are going to do is say, well, let's assume that we have some slack in our design, and given that timing, I'm going to assign my delays maybe say D1, D2 plus 5% of the minimum, and D3 plus maybe 10% of the minimum. So now if I can tolerate some discrepancy in the delays, I can certainly reduce my energy. And the question again for you is, what's the optimum sizing strategy to minimize energy under these delay conditions? And for that, I will just give you a hint in which direction you can start. If you have a MATLAB, then you read the help on this function, fmin_con. So what this does, con n. So what this does is basically it minimizes a certain function f. So what this does is basically following. Say minimize f of x subject to c of x less than equal to 0. This is basically your objective function, and this is your constraint function. In your case, this is going to be energy, and this one will be the delay. Okay? So when you basically calculate your delay, what you're going to do is basically have this vector and say my calculated delay d1, d2, d3 is less than minus, because it has to be in this form, basically d1 star, d2 star, d3 star, that has to be less than equal to this. So what you need to do is basically have another function now. So you have two functions in MATLAB. One would be you have your energy and you have your delay, and you just basically constrain them. And then finally, when you do all of this, you figure out your optimum sizing. Then the final stage is, which should take you about half a week. Basically, just plug all this into HSpice and see if you have any difference in results from your hand analysis using that calibrated delay model and your SPICE results, and sort of understand what's really going on there with the signal slopes, with nonlinear capacitances, and all of these things. So read all that in background material we posted, so that will be helpful. Any questions about the project? Everybody clear what's going on? All right, so we'll be available on the news group and in office hours if you have any further questions. Anything else? Questions about the last lecture material, homework? All right, good. So what we're going to do today is we're going to continue. If you can switch to slides for a second, thanks. We're going to continue with CMOS logic gates. And the next step is to basically understand the approach for analyzing delay in complex logic gates. We figured out the inverter. That's the old stuff. Equivalent RC, we know how to do it. That's now simple for us. But now we will see when you complicate the structure of a gate, you will have first a little bit more complicated expressions for the delay of a gate itself, and then The ultimate goal that we want to achieve is basically, well, let's make this useful. Let's analyze the gates in the context of data path. That's what we really want. When you have a chain of gates that are different complexity and stuff, how can we still do this very effectively using our hand analysis? That's what we're going to talk about today. So let me now continue with this example that we came to last time. So what we did last time is, basically just to recap in 30 seconds, is we learned the way to construct complementary CMOS gates. And the fundamental principle that we used is basically duality principle, where you can construct dual pull-down and pull-up networks. You can do so either using the Euler path approach, or you can do that using the De Morgan theorem. So basically, every time you have a function, you have, for an example of an NAND gate, you have A, B. That is your pull down. You always have this big bar on top to implement your complementary function. And then using De Morgan theorem, what you are going to do is basically apply De Morgan principles all the way to these simple terms that correspond to your signal. So you basically, whenever you have a situation like this, so you have, this means this is your PMOS, because PMOS is driven by the complementary signal. So what this tells you is basically NAND gate using this principle is constructed simply by using a serial connection of two transistors A and B to ground. This is function. And now I have parallel combination because it's a plus of a PMOS transistors, but they are driven with these complementary signals using this De Morgan principle. And that's how you construct your NAND gate. So now the next question is, let's figure out the delay of this gate. And how does this all work out? So to calculate the delay of a gate, we can establish the same way we did in the past for the inverter, a equivalent model of this gate using transistor models as switch in a series combination with a equivalent resistance. So what we are going to have over here is this representation. So this switch will be controlled by signal B. This switch will be controlled by signal A, and B. And let's assume for a moment that all transistors are the same. So we have RP, and NMOS transistors are the same, Rn and Rn. And that we have some load at the output. And in addition to that, we also have this guy, intrinsic capacitance. So now this is getting a little bit complicated for the delay analysis purpose. So now, unlike an inverter, where you have clearly defined topology for the pull down and pull up, in the case of an NAND gate, this is no longer true, because you can have both your inputs switching from 1 to 0, or you can have only one input. So you basically have all of this data dependency. So now let's see when, for example, the case when only input A switches from 1 to 0. So this PMOS is turned on, then your equivalent pull-up network is simply RP charging the load capacitance. And then you have your propagation delay is equal to 0.69 RP times C total at the output. But now let's just see, we have another situation when both of these transistors are turned on. So then you have propagation delay that is half of that, right? And then in the NMOS case, you have a totally different scenario. You have basically both of your transistors have to be turned on, and then you have basically propagation delay. Your time constant is equal to Rn times this intrinsic capacitance, because this is where you start your signal, right? This is your source. That's the ground. And then you have CL Rn plus another Rn. So you see you have not only different delays, but you also have a huge delay mismatch because of the stack of NMOS transistors. When you have two transistors in series, you have two effects. You accumulate more capacitance due to this intrinsic capacitance, and your resistance also goes up. As a result, you will have quadratic increase in your delay. That's really bad, right? And for the pull-up, when you have parallel devices, they kind of work together with each other. And by adding more devices in parallel, you will have only linear increase in delay because you're only adding up to the node capacitance. Your resistance still stays the same. So conclusion from here is, for the complex gates, delay is very dependent on the input patterns. Depending how your input switch, you will have different pulled up and pulled down configurations resulting in different delays. Questions?
Suppose my A input is 0, and then my PMOS transistor is and it's pulling up. So how is that C internal capacitance getting charged?
So let's say your A input is
0.
0. Okay.
And then how is C internal getting charged? When by discharging, it will discharge through that bottom RN.
Right.
How is this getting charged? Suppose even while pulling up, A was equal to 0, and it was pulling up only through that top one.
When A is equal to 0, pulling up to the top one, then basically this one stays at its own value. And when A has to be A basically charges this one. A has to be equal to 1, basically, because maybe it's easier to understand from this diagram over here. That's a very good question, and we are coming into that. It's a good hint. So basically, when this one is 1, then you will have a charge going into this one, charging it up, right? That's the only way you can charge it up, when this one is turned on. Another question?
Can you explain the last term with CL, RN plus RN? Is it like because of CL is in parallel with the series combination RN?
Okay, so let me, that's a good question. Let me draw another diagram for you. So let's say we have a 0 over here. Then we have Rn from this transistor B. Then there is this intrinsic capacitance sitting over here. Then we have another Rn from this transistor A. And then we have the load capacitance V out. And now we use the Elmore delay mechanism. Okay? So now you have the time constant, you see, like C int Rn plus CL times 2Rn. So the Elmore delay is a very useful mechanism to analyze propagation delay of logic networks. Okay. So now let's take a moment to analyze what's going on with all these intrinsic capacitances and the propagation delay business for the NAND gate. Because if you understand the NAND gate, everything else will be in the same manner, and we can easily generalize to more complex gates. So let's now consider a NAND gate again, when we have two pull-up devices and let's see, I'm going to label them. This would be my B device and A device. C load. Okay, so we have a couple conditions to analyze over here. Let's take a look at low to high transition at the output. And let's analyze the case where both inputs A and B go from 1 to 0. what's going to be equivalent network over here? Two transistors in parallel, right, working together. So when A is equal to 0, B is equal to 0, both of these branches will turn off. You basically have a nice and easy pull-up through the parallel combination. So let's say this is my reference delay, TP, LH, reference. Now, we have two other cases. Basically, we have a case where only one of the inputs goes from 1 to 0, and another input stays at logic 1, right? And then we have to distinguish two cases depending on the initial condition on this capacitance, internal capacitance. So let's say that first analyze a simpler case where A is equal to 1. A equals to 1, what does it mean to this intrinsic capacitance? What's the value of this node over here when A is equal to 1? 0. Okay, good. So this is intrinsic capacitance discharged. Now, when B goes 1 through 0, what's going to happen is basically this one will be turned off, and your output capacitance will be charged through this equivalent network R times C. So you have TP LH about 2 times TP LH from the previous case, from the reference case, because now you have only one transistor pulling up. So this is very fast. This is a little bit slower. And let's analyze finally the third case. So let's say now B is equal to 1, and A goes 1 through 0. So when this happens, basically you have B is equal to 1, C intrinsic is going to be charged. Right? Let's see, let's figure out what's going to be the worst case over here. When B is equal to 1, C intrinsic is equal to charge. Okay, so now C intrinsic is going from discharged to charged, right? Because when A was equal to 1, then initially this capacitor is discharged. Does that make sense? And then when A goes 1 to 0, B stays at 1, what you're going to have is basically the following network. So you have this transistor is charging on the capacitance CL, but also this transistor is turned on. So you also have to charge this intrinsic capacitance. Now, since you have to charge more capacitance than you had in the previous case, when you only had A going through this load capacitance, then basically your propagation delay is going to be the slowest. You have the longest propagation delay in this case. Everybody understand this? Questions? So basically, in one case, let me do this. So in case A, you have this. You have two parallel PMOS transistors charging up CL. In case B, you have only one transistor charging CL, and in case C, you have one transistor charging CL and another transistor charging intrinsic capacitance. Remember the Elmore delay formula? When you have a configuration like this, you have time constants from these off-path guys. So that's the example we did a couple lectures ago. So this is basically your Elmore delay. What's going to be your Elmore delay here? Anybody? So if this is your R, this is your R, and this is your CL. So CL time R plus C intrinsic C is also this common R, right? Okay. Good. Everybody clear with this? Uh-huh.
Why do you have C intrinsic only between A and B? The NMOS, or do you just put it there?
That's a good question. Question is, why do you have intrinsic capacitance between only between A and B? Basically, intrinsic capacitance exists also over here as well, but we just lump it into this load capacitance. And over here, we have to say, well, explicitly, I have another capacitance that's really sitting here. And by the way, what's the value of this intrinsic capacitance? Where is it coming from? Ideas? So let's say that this transistor is M1 and this transistor is M2. So let's now see what is the C intrinsic equal to. What are the capacitive components that factor into this C intrinsic? Okay, drain body, that's one. So we have drain body of this transistor M1, right? Anything else? Then you have source and bulk of transistor M2. Another one. Gate drain from M1. This is the gate drain from M1. That's correct. Anything that needs to be here? Is this just the gate drain? Is there anything else? 2 times. Miller effect, right? That's when input A switches, then you have this node swinging in the different opposite direction. So Miller effect. All right. Great. And for the low, let's go now back to slides. So this is basically showing you what we just discussed. When you have both inputs going from 1 to 0, this is the blue line over here. This shows you the voltage at the output for 3 different cases. When both input go from 1 to 0. Yes, question?
What about the gate source for the other transistor?
Gate source for the other transistor. Let's see if we forgot anything. Going to, thank you. So gate to source. Oh, GS, correct. Good catch. Gate to source of transistor M2. Okay, thank you. All right, so let's go quickly back to slides. So this basically shows you the 3 different cases. When you have 1 to 0, propagation delay is 35 picoseconds. When you have only one PMOS pulling up the C load, nothing goes with the C intrinsic business, you have a little bit longer delay, 57. And then finally, when you're charging both of these, in the worst case, you have this delay of 76. So you see you have 2x difference in propagation delay. Now you can work also the other example for high to low transition. And in this case, you will see a surprising result that if you have both of your inputs switching at the same time, you have the longest delay. Right? You can work through the example. It's basically also considering this switched capacitance, intrinsic switch capacitance, that will give you the idea. Basically, what's going on, why is it longest delay? Because when you have both of your A and B switching, during the initial period of your transition, you will have also both of these PMOS transistors on top turned on, right? And you'll be fighting them a little bit for a short period of time until they turn on. You fully turn on basically your NMOS devices. And then from that point in time, you have to basically discharge 2 capacitances. You have to discharge your load capacitance and also your intrinsic capacitance. When one of the transistors is already set, basically, let me illustrate that real quick. So basically for the high to low, if this was at 1, This means that this capacitance was discharged, and when this one goes 0 to 1, it will only have to discharge the load capacitance, and this is going to be really fast. So you basically have, this is virtual ground, and then you have CL, versus the case when the other one was 1. So then the other one was 1, and then you have to basically discharge both of these capacitances. This one was at 1, and then you're discharging this guy and discharging this guy. And finally, in the last case, you're also going to spend some time to establish this one, because it's not 1 to begin with. So you have to spend some time turning that transistor on, resulting in even longer propagation delay. Okay. Good. So now the question obviously becomes, well, this is really getting out of hand. This is ugly. I mean, this is just a NAND gate. How about more complex gates, like 3-input, 4-input gates, different logic functions, topologies? It's going to be really difficult. So let's now try to understand a little bit what we can do with our gates to make propagation delay about balanced in the worst case. So if you have a NAND gate, and what we want to do is, let's try to get the first order estimates of transistor sizes that will give me about the same pull up and pull down as my inverter, and in the worst case. And I want to compare this to that guy. So let me assume that for a symmetric inverter, I have PMOS 2 times wider than the NMOS. That gives me the same equivalent resistance. Now, question for you. How would you size these two pull-down transistors to have the same equivalent pull-down resistance as an inverter? Talking only about resistance here. How much? 1/2 of the inverter? What happens with the resistance when you put 2 transistors in series? It adds up, right? So how would you size? What's the impact of gate sizing on equivalent resistance? What do you need to do to... Was that? Correct. Okay, everybody got that? So basically you have to double these two such that you have R over 2 and R over 2 resulting in net equivalent R. Okay. How about the PMOS pull-up? What do you need to do to make the same pull-up as inverter? What happens in the worst case? Only one transistor pulls up, right? Forget about this intrinsic, forget about all other stuff. First order. 1/2, why 1/2? But what's the worst case? That's the best case, right? You want to size your transistor such that you're sure that your delay is going to be certain number under worst case conditions. Any? Make it as big as inverter, right? Because that's the same pull-up resistance. How would you do the NOR? If you have a NOR, how would you size these two then? One on both sides, correct. And then for the pull-up, 4, correct. Because you want to make the same as the pull-up resistance of this one. Okay. So now you get the idea, basically. When you have series connection of transistors, you need to upsize them. When you have parallel, don't do anything. Okay. And let's go to slides now to do another example. So how would you size this complex CMOS gate such that it has the same equivalent pull-down and pull-up resistance as CMOS inverter? Same principle, basically. So how about this transistor D? So it's basically one of the parallel branches. So basically it is still 1, right? Because for parallel branches you don't need to do anything. For serial branches you need to upsize them. So now how about this transistor? So basically, since it's in a serial branch with the other 2 transistors, you have to upsize. And then the same thing for these other 2, because only one of them conducts in the worst case, right? And then for the pull-up network is basically the same strategy. You know that this one is in serial connection with the rest of the network, so you double that. And then for the other transistors, you also have basically the same value if only A and D are turned on. So it's basically the same as your NOR case. And then you have these other 2 that have to be further upsized because they're in series with each other. Okay? Does that make sense? All right. Question?
Are you ignoring the effect of intrinsic capacitance?
Correct. Yes, intrinsic capacitance is ignored for now because it was really complicated just to get us first-hand analysis. But now we are actually coming back to your question from last lecture. So basically, when we have a fan-in consideration over here, so if we apply the Elmore delay model to this network, so what is going to happen for this four input gate over here? Let's do the pull down quickly. So we have intrinsic capacitance C1, C2, and C3. So let's now assume what Peter just pointed out is basically we have the same size, all the transistors are the same, and basically what would be my Elmore delay to this point? So what does C1 see? C1 times only R plus C2 times what do I see? So let's see, this is R1, R2, R3, R4. So this is R1. So this is now R1 plus R2 plus C3 sees everything that's basically back upstream because this is our source over here for the delay calculation analysis. This is our source node, source voltage, and this is our output. Okay, and then C3 sees R1 plus R2 plus R3, and finally C4 sees R1 plus R2 plus R3 plus R4. So now you look at this R1 guy, poor guy, he has to carry all the load. He has to go to C1, C2, C3, C4. C load, that will be C4 over here. Right. So what this tells you basically is that two things. One, you first have quadratic increase in your propagation delay because you have both R's and C's adding up to each other, right? And second, now the question is, how would you now change your sizing strategy starting from all transistors being the same such that you have a little bit better delay than you have in this case? What would you do? What would you do to this guy? Would you increase its size or decrease its size? Correct, because when you increase the size, you reduce the equivalent pull-down resistance. And that helps you a lot because this R is all over the place, right? And that's actually what people are doing. When you have a stack of devices, then the sizes will go something like this. Basically, you will have this one will be very wide, this one will be a little bit narrower, and so on. So you have a progressive size increase going from the output back to the input. And also this works well because for the capacitive component intuitively, right? Because when you're getting closer to the output, you're reducing the amount of this parasitic capacitance, correct? That means you're also making your delay faster. So that kind of works well for both cases. But now this comes to the question from the last lecture, basically. Now, assuming that you are doing your transistors horizontally, they have different widths. So what you're going to do with your diffusion over here? So what this implies, basically, if you had a case where all my transistors are basically the same width, I'm good with that. And these are my poly lines. So now let's assume that I have to make these transistors progressively larger as I go from the bottom up to the stack. They're the largest one is at the bottom. Then I have to step down a little bit in diffusion, and then I have to finally proceed with the last one. And now what this is going to influence is basically I'm going to end up in overall a little bit wider cell, because I have all these constraints from the design rules that there should be some enough spacing between diffusion and poly and so on. So this, as a result, basically, it buys you performance. It offers you better performance, certainly, but you have to pay a little bit of price in area for the same total overall sum W. If you sum all the W's here, sum all the W's here, they're equal. This one area is a little bit increased because of these design rules and things. Okay. All right, so let's go now back to slides. I have a plot for you to illustrate the propagation delay of this NAND gate that we've been analyzing thoroughly. So as we mentioned, low to high delay is linear with increasing number of fan-in stages. Because when you increase the number of fan-in stages, you basically just increase the number of parallel branches. And in the worst case, only one of those parallel branches is conducting and delivers current to the load. So basically, you have linear increase with the fan-in. Increase the number of inputs, your delay goes linearly. For high to low transition, you have increased pull-down resistance, you have increased capacitance all over the place. So your delay goes up quadratically. And the typical rule, looking at this graph, is that basically gates with fan-in greater than 4 should be avoided. So now in the next couple illustrations, we will see what are some of the techniques that we can implement efficiently gates with the large fan-ins. This is another thing over here. What happens if you increase the fan-out? Let's say now we keep the fan-in the same. So basically what you're going to end up with, that's basically translating into only increasing your load capacitance. You fix your pull-up or pull-down resistance, and now you just keep increasing and increasing load capacitance. Since this is RC delay model, you basically have linear increase with the fan-out, because your capacitance increases linearly. And now what we are going to see a little bit later in this lecture is basically that there are different slopes for the inverter, for the NAND, and for the NOR, because of the equivalent pull-up and pull-down resistances. But basically, this is a linear fashion number. So that's basically the same formula. TP is equal 1 plus fan-out divided by gamma. So what is this value? If you extrapolate this all the way down to 0, then you get your TP naught. And then from here, you have this slope. So this is how this could be modeled, basically. We said fan-in is a quadratic, fan-out is approximately linear. This is how you model your propagation delay. And this is what we also discussed. You have progressive transistor sizing. When you have a long stack, you would want to make M1 the biggest, and then you decrease the size gradually. And you can, this is a good technique, but it can't really buy you much in delay, maybe 10% or so. So just be aware of that. Another thing is, as we discussed, how do you improve the speed of your gate? Basically, let's assume that we have a certain configuration over here of pull-down stack. And let's assume that our critical path goes through the bottom transistor. And critical path means basically signal that triggers your gate the latest. That's the laziest signal, basically. I arrived late, sorry, you need to wait for me, and we can then propagate. So basically, you want to make sure that that signal is propagating through the network as soon as you can. So you basically say, okay, you arrived late, I'm going to bypass you, put you through the fast track. And this is what's happening here, basically. You want to take advantage of these conditions on the other transistors. So let's say if I have inputs 2 and 3 that are already settled to 1, and then I'm just waiting for this input 1 to discharge all of the capacitances. No, let's not do that. Let's do some work before that input arrives. So if I just reorder these transistors in a way that I have inputs already settled at 1, then I'm discharging C1 and C2. So all that this lazy guy has to do is basically discharge the big capacitance. Don't deal with all of these, right? And that will improve your delay, right? So that will be delay is determined by the time needed to discharge this final capacitance and make sure that you order your inputs in appropriate way. So that's option number 2. Option number 3 is, as we saw, fan-in is really bad. When you have a large fan-in, so the good idea for that is basically to distribute this fan-in. And you break it up into gates with smaller, fewer inputs. So let's assume what we have over here basically in the NAND gate. So let's assume we have a really wide NAND gate over here with number of inputs n. And then we have an inverter following that. So what we can do is basically break this up into 2 equivalent branches. And then we have a NOR following that. But now the number of inputs in each of these branches is equal n over 2. Okay? N over 2. So now I know that in the worst case, pull down of this guy is really bad. So that's the reason why I'm doing all of this. So pull down of this guy is basically proportional to this n squared. And that's really hurting me. So now what I know is that CMOS logic is complementary. What this means is that if I have pull up over here, I'm going to have pull down over here, and then I'm going to have pull up over here. Now when I'm cascading the gates, basically the bad pull down of this guy is cascaded with the bad pull up of this guy. But it's still better because over here I have n over 2 squared plus only basically 2 squared, right? So if I had 8 inputs, I had 64, and over here I have only basically 8 divided by 4, so it's 16 plus 2, so that's 18. So that's a huge delay saving. So logic restructuring can also help you do a very good job with propagation delay. And as a rule of thumb, in real design world, you will normally deal with 2 input gates, very rarely with 3 and higher input gates. So it's like 2 or 3 inputs. That's a good number. All right. And also, finally, this is another technique for which I have an illustration over here, is when you have a large capacitance, we already know, we just insert a buffer, right? It's good to distribute the effort into many stages. Basically, just gradually develop the voltage on that final output node. And finally, this is the technique that we also mentioned with the pass transistor gates, which we're going to talk about next lecture. Reducing swing is always good because basically it gives you smaller delay, but it hurts the delay of the next stage. So this is applicable only in certain cases, such as in memories where you have sense amplifiers that react to very small changes in the input, differential pairs. So that's good. Otherwise, not very useful technique. Now, finally, you see that this is getting really complicated. Okay, just analyzing simple gates is really bad. And how about chains of gates? That's going to take you really some time. You have nightmares. But luckily, people have developed this really nice theory of logical effort. And this is all based basically on the following assumption. Basically, you say, I know how good the inverter is because I know how to calculate propagation delay. I know how to calculate everything for an inverter. I'm very happy and familiar with that gate. If you give me more complexity, I'm stuck. And what this concept actually tells you is it compares the gates to that inverter and say how much, just given the topology of a gate, for example, a NAND gate, how much more effort my NAND gate has to spend due to its complexity to deliver the same pull up and pull down as an inverter and make sure that I still have basically the same inverter-like performance. And that's called the logical effort. Basically, it's related to the logic function compared to an inverter, and basically it tells you how much effort extra effort my gate has to spend to be equal to that on inverter. There is a whole book written about this, and if you tried reading this from your textbook and got confused, that's what's really expected. When I really read the entire book of logical effort, then I read the textbook material on logical effort, I was confused too, because I thought I knew the material. So basically I went around and looked for some material to basically help you understand this. And this is just basically the idea. This little chip guy who is really confused, he's stuck the same way as we are now. He's dealing with very complex problems in his life. Gates, I don't know what to do with them. So now I have a lot of questions basically for a data pad. What's the best circuit topology for a function? How should I size these transistors? How many stages should I have for least delay? And I really have to make some important decisions. Luckily, logical effort is a method to answer all of these questions. It uses simple delay model, usually quoted as back-of-the-envelope calculations, to sort of figure out first-order business. And it's useful to everybody who basically do the simulate tweak loops, circuit designers, high-speed designers who really need to know where is the delay going into their logic, and CAD designers who want to develop better tools. And so in the next 5 minutes, in these 4 slides, I'm going to teach you everything you need to know about logical effort. If you want to read the book, or that's fine, but this is really the core of that. And you may find a little bit confusing notations in the book and all over the place, so I'm just going to use really simple notations for parameters that are not confusing. And this is the reasoning that we start from. So we know that delay of a gate is equal to 0.69 times the drive resistance times intrinsic capacitance times 1 plus this C out divided by gamma times C input. And this is equal to TP naught, 1 plus my fan out divided by gamma. Okay? So now, since you're really dealing with gate capacitance, because that relates to the sizing of your gate, you would rather really like to work with the gate capacitance than the intrinsic capacitance. Intrinsic capacitance is good. It tells you what's your propagation delay TP naught of an unloaded case, but that's rather unrealistic case. It's just some time constant for a gate. So let's write this delay in a different way. So let's say my delay is equal to 0.69 R drive, and now I'm going to use C gate. If I use C gate, what I'm going to have over here is basically gamma plus C out over C in. So it's basically just saying that C intrinsic is 1 over gamma C gate, and then we do it here. And then this parameter over here, I'm just going to say that this is tau gate. That is some time constant for a gate. And this is simply the fan out. People use various notations, use H, use F, that's a fan out. Everybody knows. FO. So now let me go one step further over here. Everybody happy with this so far? Okay, good. So let me now analyze a case where I have following example. So this is stage J plus 1, and then I have this J plus 2. So now in this example, what would be my delay? Delay would be equal to this tau of a NAND times. Now I have this parasitic capacitance of a NAND gate, the ratio of these parasitic elements, plus J plus 1 divided by Cj. And then I have tau for inverter times gamma inverter plus Cj plus 2 over Cj plus 1 plus tau of NOR, gamma NOR plus Cj plus 3, which would be the next stage, divided by Cj plus 2. Now, as I said, we are really happy with an inverter, know how it works. So let's now normalize this delay to an inverter delay. So what we are going to get over here is divide this by tau inverter. Tau inverter. And let's do a little bit, since these equations are still hard to fit on the back of an envelope, right? Because it's a lot of things for just simple three-stage circuit. We need to do define some new symbols. So what I'm going to do here is write this out following way. So I say this is now equal to my normalized delay. This parameter is now basically equal to my logical effort. So the ratio of the time constants of a gate and inverter, that's basically the logical effort. And that's going to be clear in a second. Why is it so? And then I have this fan out. And then I have another parameter that's called PNAND. So what I'm going is a bunch of these transformations over here. This is now logical effort times the fan out, and then this logical effort times this gamma. That's basically my PNAND. So what I call over here is, this is basically logical effort. This is simple fan out. And this is parasitic delay. Okay. Everybody all right with this? Okay, good. So what this tells you is basically parasitic delay is now your former TP naught, normalized to that time constant tau. So it basically just gives you the delay of your gate that is unloaded. And this is now the fan out delay. So it basically relates to the complexity of a gate and your fan out. So, and this is very important parameter that kind of puts all this into a sensical form. What logical effort tells you is basically what is the ratio of the total input capacitance of a gate to the input capacitance of an inverter, such that you have the same delay from that gate as the case in an inverter. Or you can basically look from the other perspective. If you have the same input capacitance, how much worse is your delay from the perspective of the pull-up and pull-down resistance than your ideal inverter? Because we know inverter is the best driver we can have, and we can basically quantify all other gates relative to the inverter case. So let me now switch to slides and basically review all these steps. So first thing is, forget about C intrinsic. Let's express everything in terms of C gate. That gives us this formula. Then you normalize that delay to the time constant of an inverter, and then you write it into this expression. That is still too complicated. What happened with this equation? Okay, good. So then you introduce a couple more symbols, and then you come up with this very simple formalism for delay calculation. And this way, basically, delay of each gate has two components: effort delay and parasitic delay. And as I mentioned, there is a couple options to find logical effort of a gate. One is to set equal pull-up and pull-down resistance, R drive is equal, and then compare the input capacitances. And then set C in equal compared the R drive. Or basically you can just start from the basic principles. You know that the logical effort of a gate is equal time constant of a gate when it's unloaded versus the time constant of an inverter. And then you basically just know that the time constant, the way we defined it, is drive resistance times the input capacitance divided by of a gate divided by that of an inverter. So you basically derive now the ways to understand this logical effort. Now I know this is still not clear. Let's do a couple examples. So let's do a NAND gate. So we say that we have an inverter. That's our benchmark gate, 2, 1. And then we have a NAND gate. If this is our input A and this is our input B. So now we already know how to size this for the same pull-up and pull-down resistance. Let's ignore all these extra capacitances. So for this guy, we know that this should be 2, 2, 2, and 2. Now what's the total capacitance looking into this node? C in is equal to how many? You have this transistor and this transistor, right? So it's 4. Okay? And then the total capacitance looking into this inverter is equal to 3. Now, this is the sizing for the same pull-up and pull-down resistances. So what this means is that the logical effort of a NAND is equal simply to the capacitive ratio that provides these conditions. So it's 4 over 3. Okay, so let's do the NOR gate. So in the NOR gate, we also have 2 inputs, A and B. See, this is B, this is B. And then the sizing of the NOR gate would be 4, 4, 1, 1. So the logical effort of a NOR would be what? 5 over 3, correct. So you see that you can sort of understand which gates are good. So you see the NOR is a little not so good as the NAND because it has a stack of these PMOS devices. As a side comment, dealing with complex gates, you may find a situation where logical effort is not equal for all the inputs just because of the complexity of a gate. And let me do one example to illustrate that. So let's say we have a gate like this, and then we have another PMOS over here that goes to this input, and then we finally have 2 more NMOS transistors. One is connected over here, and then another one goes there. So we have A, B, C, and this is our output, Y. So sizing of the gates, have stack of NMOS transistors, double the size. These 2 can conduct only one at a time in the worst case. This one goes 2, double the size over here because it's serial. So now let's see what the logical effort of input A. That's equal to total 4 plus 2 is 6, divided by 3, that's equal to 2. Logical effort of input B is equal 4 plus 2, that's 6, also 2. And logical effort on input C is equal to 2 plus 2, 4 over 3. Right?
So
for A,
Okay, for A, what does A see? So it says this one and this one. And then we know that the input capacitance of an inverter is always 3. That's our normalization. So this is equal 6 over 3. Stage B, what's the capacitance that you see from here? So you have 4 and 2, 6. And then finally this tricky guy over here. It's actually a good guy because it doesn't take too much effort. So you have 2 over here and another 2 over here. So that's 4 over 3. Okay? And then for the parasitic delay, what you need to basically figure out is just to find the ratio of the capacitances that are connected to the output. So over here in red, I'm going to do the parasitic delay. So basically, the parasitic capacitance that's sitting over here is basically the sum of all the widths of your transistors. And that's divided by sum of all the widths that's sitting at this node for an inverter case. So what do we have here? We have total 6 divided by 3. So we have parasitic for the NAND is equal to 6 over 3 is equal to 2. How about NOR? NOR we have to look at this node. Right, we have 4 and another 2, so we have still the same situation. So 6 over 3 is equal to 2. Now when you add more inputs, what's going to happen with, let's say, P NAND with M inputs? So when you have M inputs, what this means is basically you have M of these in parallel, right? So you have M of these in parallel, and then since you have a stack of M transistors, each transistor has to be upsized by a factor of M, right? So you have total is equal to M, plus you have 2 times M, because all of these PMOSs are wide 2. Okay, so you have 2 times M divided by 3, so you basically have parasitic of this guy is equal to M, right? How about logical effort? What would be the logical effort of a NAND with M inputs? So what you have is basically looking into a capacitance of each of the inputs. You have 2 from the PMOS, and you have M from the NMOS. So it will be M plus 2 divided by 3 from an inverter. Okay? For the NOR, you can do the same analysis pretty much. You can basically, this one is now going to be the 4M, and you will have all these M's down in the bottom. Everybody understand this?
Can you explain like why you get, like P NAND equals like 6 over 3 and 2? Can you like why that on the
P NAND is equal to, this is the 2-input NAND. So what you need to do is basically go around this node and see what's the total transistor width of all the transistors that are connected to this node, because these will contribute to parasitic capacitance, right? So you have, if you position yourself over here, you have this one, and this one. So it's all 6. And then you have to normalize that to an inverter. Okay? Good, so let's go over to slides over here. So this is basically a catalog of gates. This is a logical effort in some common gates found. We assume that logical effort of an inverter is by definition equal to 1. And then you can figure out the NAND and NOR. For example, for N stages, you have for NAND is equal N plus 2 divided by 3. For a NOR, you have 2 times N plus 1 divided by 3, because now you have a PMOS that are stacked up, and then you have pull down NMOS. And these are the parasitic contributions. So let me do one more thing, and then we'll finish this off next time. You can page through the examples that you have in the notes, and I'll come back to that, revisit it next time. So this is what happens when you take into account fan-out, and this is a way to estimate logical effort and parasitic delay from simulation data. That's what really people do. They calibrate an inverter, figure out what's the slope of the delay versus fan-out curve, and say, well, if that is 1, then I'm actually normalizing all my other gates to the inverter. So over here, what I plot is basically an inverter and a 2-input NAND gates. Now for the inverter, what is the logical effort? By definition, it's equal to 1, right? Parasitic delay is also equal to 1 by definition. So the total delay is the sum of these two, and I apologize for the notation here. So it's basically just this fan out plus the parasitic delay, because logical effort is 1. Now over here we have logical effort is 3, parasitic delay is equal to 2, logical effort is 4 over 3, sorry. And then finally you have the delay is equal to 4 over 3 times fan out plus 2. So the slope of this curve is logical effort, and the intersection with fan out equals 0 is your parasitic delay. Everybody fine with that? And let's just do one more warm-up example for next time. What is a logical effort of this structure? If you just need to determine delay of only one gate in this configuration, what's the logical effort of this gate? It's by definition equal to 1, right? What's the fan out? It's also called electrical effort. So it's basically the ratio of the output capacitance of this guy to the input capacitance. If all these inverters are the size the same, then it's 1. So parasitic delay of an inverter is also 1, correct? That's definition, P int. So now the stage delay is equal to logical effort times the fan out plus the parasitic delay. So total stage delay is equal to 2, and now you can basically estimate your oscillation frequency. You know that 2 times this delay relates to the cycle times n, and this is equal to 2 times tau, so you have this number. So it's really nice and easy way to get delay analysis in your circuits. We'll continue this on Thursday.